Okay, so I think it's a good time to say a few words to start. This is our first experiment to have a morning seminar here in Boston, hosting Ian Jauslin in Princeton. The idea of having it in the morning was that people could join us not only here, but easily in Europe and with some late time in China. And I see that we have somebody from China already in the meeting, and that's wonderful that we have this experiment, and maybe it will be successful and we can expand it at some future point. The talk today is by Ian Jauslin. Ian's now a postdoctoral fellow at Princeton. He came from the University of Rome, where he worked with Alexandro Giuliani and other people. And we're very happy to hear about his current work with Heilmann-Lieb on liquid crystals and the Heilmann-Lieb model. So Ian.
Thank you. Thank you very much, Arthur, for the organization, and thank you for Yunshang. Thank you to Yunshang for setting up this meeting. This is all kind of new to all of us, and it's great to see that we can still do some good work even in the current situation. So I'm very happy to be here, be it virtually, and I'm very happy that you guys all tuned in, and I hope we're gonna have a good time. So yeah, I'll be talking about a project that I have with Heilmann-Lieb from Princeton University, and it's a project about liquid crystals. I'm going to define in some detail what a liquid crystal is, but first, before I do, let me just go through a little, some more down-to-earth things. So if you turn your attention to the bottom of the screen, there's an archive number. That's the archive number for the preprint that goes with this result. So if you're interested in details about what we've done, you're invited to have a look at the paper, which is available among others on the archive with this number over here. I also usually like to write down the URL for my website, which is down here. On the website, you can find not only the paper here along with the source code for the paper. I also figured I'd put the slides of this talk on my website. So if, for instance, I'm going too fast through the video, if the video is not clear, you can go to ian.jauslin.org and download the slides yourself, and you can follow them alongside the presentation if you would like to. On the website, you also have, so there are going to be some figures coming up. There's the source code for the figures and so forth. So you may be interested in such a thing. Anyways, so let me get into now the nitty-gritty of the subject, and let me tell you what a liquid crystal is. And to get to liquid crystals, I'm going to start with something much simpler. I'm going to start with just liquids and crystals. So I'm going to give a brief overview, not so much of what a liquid and a crystal are, but rather what the words liquid and crystal are going to mean for this talk. But I'm going to start very basic and say something that is probably known to most of you, which is that a lot of compounds that you may know and have around you come in several different phases. For instance, if you think of water, water comes in a liquid phase at ambient temperature, but if you heat water up above 100 degrees Celsius, it becomes a gas, and if you freeze it below 0 degrees Celsius, it becomes a solid. And these three phases, the gas, the liquid, and the solid, they're all very different even from a macroscopic point of view. They're qualitatively different from a macroscopic point of view. A gas, from a macroscopic point of view, occupies all the volume that is given to it. If you have a small source of gaseous water, of water vapor in the center of a room, that water vapor will occupy the entire room. Whereas crystals and liquids are so-called condensed phases, where the volume of the water becomes limited and the water becomes incompressible. Now, liquids and crystals, so liquid water and crystalline water are quite different, mostly in that liquid water has many more degrees of freedom, in the sense that liquid water flows. So if you pour water into a glass, it takes the shape of the glass. It doesn't have a predefined shape, whereas ice has a very well-defined shape, and that shape cannot be changed other than by breaking the crystal. So from a macroscopic point of view, these three phases are very different. The object of the talk here is more to focus not so much on is to focus on these macroscopic properties, but to see how they come from the microscopic structure of these different phases. Because from a microscopic point of view, the difference in these phases is rather subtle. For one, when you have three different phases of water, the basic molecule that you're looking at is still water. It's the same in all three phases. And so this same molecule can have very different properties in these different phases. Now, the way that I'll characterize the difference between these phases from a microscopic point of view is the following. So in a gas, which is the situation that's depicted over here, can everyone see my mouse? Is that visible to everyone? I assume that's a yes. So over here on the left, I have a picture of a gas. In a gas, you have molecules which are very far from each other. The density of a gas is very low. And since the molecules are far from each other, they will interact with each other rather weakly, because molecules only interact when they're relatively close to each other. So in a gas, from a microscopic point of view, you have a collection of several different molecules which are acting as if the other molecules didn't exist. So you have essentially a superposition of single atom or single molecule behavior and a bunch of molecules that have this same single molecule behavior. Now in the liquid, which is the situation that's depicted over here, the density is much higher, so the molecules are crammed together a lot closer, and so they're interacting very strongly with each other. However, even though they're interacting strongly with each other and they're restricting each other's motion, each molecule still has its own degrees of freedom. So each molecule can rotate around the other molecules, and they can move one with respect to another, and they can move one with respect to another. In contrast, if you have a crystal, which would be the phase that is depicted over here, the molecules are all rigidly stuck to each other. The idea being that in ice or other crystalline phases, the molecules or atoms tend up to occupy the vertices of a very regular, usually in fact periodic array of a very regular and periodic array that underlies the structure of the crystal. And this very simple microscopic picture explains the difference in the macroscopic properties, in that in a gas, the molecules don't really see each other, so they don't really care where the other molecules are, so there is no shape, and so the gas has no shape, and the gas has no volume either, because the molecules are just going wherever. In a liquid, because of the fact that there is no strong restriction in the degrees of freedom of the molecules, the liquids can flow. Whereas in a crystal, because everything is so rigidly packed and rigidly tied, and so since all the molecules are rigidly tied to each other, a crystal will have a well-defined shape and very few degrees of freedom. Now, the aspect of these three phases that I would like to focus on today is that a crystalline phase is a phase which I would call an ordered phase. It's an ordered phase because the relative position of the molecules is very predictable. It's very ordered. Whereas a gas or a liquid are disordered in the sense that there is no long-range correlation between the positions of the different molecules and the different atoms in a liquid or a gas. So really, from the point of view of this talk, what a crystal is, it's a system that in a phase that is ordered, whereas a liquid is a phase that is disordered. So now, when you think of things that way, well, the term liquid crystal instantaneously turns into an oxymoron. A liquid crystal would mean something that's ordered and disordered. So let me get into how that can be possible. And the idea is that a liquid crystal is now a phase of matter in which there are some properties of ordered matter and some properties of disordered matter at the same time. Now, how does that come around? Well, liquid crystals typically occur in systems of molecules that are very anisotropic. So for the sake of example, let's consider the types of molecules that are drawn on this slide over here, which are shaped like rods. Shaped like rods means that they're very thin, they're very long, and they're very straight. So you have these long, straight, rigid molecules. And the idea of a liquid crystal is that there's order in some degrees of freedom and disorder in other degrees of freedom. Now, I drew two examples of liquid crystal phases here. The one on the left is the simpler one. This is a phase in which there is long-range order in the orientation of these molecules. So in this sample, the molecules are all pretty much pointing in the same direction. But there is no long-range order in the positions of these molecules. The location of the center of each of these molecules doesn't follow a regular pattern. And right, it doesn't follow a regular pattern. Now, so this is an example of a liquid crystal phase over here where everyone is aligned, but the positions are disordered. This on the right is another example of a liquid crystal phase, which is a bit harder to see. So let me try and describe what's going on in this phase. What's happening here is that there's several different planes that are superimposed on top of one another. And on the lower plane, the rods are also, the molecules, they're all pretty much aligned, but their positions are disordered within the lower plane. And then on the next plane, again, the molecules are aligned, but the directions of those molecules is slightly different from what it was on the bottom one. They're slightly rotated. And on the next plane, it rotates more, and the next plane, it rotates more, and so forth. So you have this stacking of these different planes where the dominant direction of the molecule is rotating as the planes go up. This is called a chironematic liquid crystal. And now, this microscopic structure for these liquid crystals actually gives them non-trivial macroscopic properties as well. So this superposition of disorder in the position and order in the orientation from a microscopic point of view means that from a macroscopic point of view, these systems behave like liquids because they're microscopically disordered, so there's no constraint on the relative position of the molecules, so they can flow like liquids. You can find online, you can find videos of liquid crystals being synthesized, and they form droplets that really look like droplets of water or of any other liquid. However, the orientational order comes with non-trivial optical properties. Now, I'd like to just make a quick comment on how non-trivial this notion of order is in this case. So when I'm talking about orientational order, I mean that most of the molecules happen to be aligned, and this happens over extremely long distance scales. So for instance, if you have a sample of a liquid crystal in a beaker on your desk, you might have 10 to the 20, 10 to the 21, 22, or 10 to the 23 molecules, and they're all pretty much pointing in the same direction. From one side of the sample all the way to the other side of the sample, you have literally tens of millions of molecules that are all pointing in the same direction. And since they're all pointing in the same direction, this gives them non-trivial optical properties. So for instance, it's possible to manipulate the color of a liquid crystal or by changing the position of these molecules. It's also possible to manipulate light using the polarization of light using these liquid crystalline states. And in fact, these optical properties are the reason that liquid crystals have become quite important in technology. And in fact, I'd be ready to bet that most of you are looking at liquid crystals right now, given that a lot of display technology is based on liquid crystals. You might have heard the term LCD, which stands for liquid crystal display. So if you have an LCD, then you're staring at liquid crystals right now. In addition to technology, liquid crystals are also present in nature. There are chemical compounds that are naturally shaped like these long molecules that form liquid crystalline phases there are biological systems that have liquid crystalline phases. The membrane of cells, for instance, is a liquid crystal, and so forth. So understanding these phases is quite an interesting problem, both from the point of view of fundamental physics and from the point of view of applications. Now, when I say understanding liquid crystals, what I really mean, and what I'm going to focus on for the rest of this talk, is perhaps the most elementary question one could ask about these liquid crystals, which is, how can these phases occur in nature? What kind of mechanism does one need in order to get these phases? And a more precise mathematical question would be, can I come up with a microscopic model, so for a model that accounts for the positions of these molecules, in which I can prove the existence of a liquid crystalline phase? Now, this question is a non-trivial question, and it has a fairly long history. And it dates all the way back to a seminal paper by Lars Onsager from 1949, which is this paper over here, where what Onsager set out to do was to try and understand the mechanism that would allow these molecules to align. And the basic idea, the basic principle that allows this alignment is that if there are enough molecules around, if the density of molecules is sufficiently high, then they don't have so much volume. Each molecule doesn't have so much volume, and to pack more molecules into a smaller volume, it's just more convenient. You can fit more by aligning them. And building on this idea, Onsager wrote a paper where, starting from a microscopic model, he worked his way towards showing that there should be a liquid crystalline phase. However, this paper has really great ideas, but it's non-rigorous in that, in order to go from the microscopic model to the macroscopic properties, Onsager had to introduce a number of uncontrolled approximations, so he didn't provide a proof of the fact that there is a liquid crystalline phase in this microscopic model. So to start seeing some more rigorous work on these liquid crystal models, we have to fast forward all the way up to 1979, when Heilmann and Lieb, so Ole Heilmann is a chemist from Copenhagen University, Elliot Lieb is a mathematical physicist from Princeton. So in 79, Heilmann and Lieb, they introduced a model, which is a simplified microscopic model. So it's a model for the molecules in a liquid crystal, which is slightly idealized, in which they set out to actually find a proof that there is a liquid crystal phase. So before I go through more history, let me tell you a little bit more about what this model is and what kind of simplifications we're doing to introduce this model. So first of all, the Heilmann-Lieb model is a two-dimensional model. So as I mentioned, it's simplified. We're trying to find some model where we can say something, and the main simplification is that it's a planar model. Now, in addition to being planar, and this second simplification is actually more important, in addition to being planar, this model is a lattice model, in that the positions and the orientations of the molecules in this model are going to take discrete values. So in order to define the model, I start by drawing this grid. This is just a square grid. It's a Z2. It's a Z2 lattice. And on this grid, I'm going to put so-called molecules. And the molecules are going to be so-called dimers. A dimer is an object that occupies an edge of the Z2 lattice and the two adjacent vertices, with the constraint that no vertex can be covered by two or more dimers. So there's a repulsion between the dimers that prevents two dimers from covering the same vertex. Now, for those of you who may be familiar with dimers from the point of view of combinatorics, this model would actually be called a monomer dimer system, because there are some sites over here, like these, which are not occupied by a dimer. And generally speaking, in combinatorics, one says that these sites are occupied by a monomer. So from that point of view, this would be a monomer dimer model. Since I'm focusing on the position of the molecules, and the molecules are represented as dimers, I tend to call this a dimer model. Anyways, so you should imagine that these that these little dimers, these little dumbbells here, represent the molecules. Now, these molecules, they have a position, which is discrete, but they still have a position. That position would be, say, the position of the most lower left vertex on the dimer, and they have an orientation. Specifically, the orientation here is dimers can either be vertical, like this one, or horizontal, like that. So dimers have a position and they have an orientation. So it becomes a well-defined question to ask whether in this dimer model, one has a liquid crystalline phase, which means do we have long-range order of the orientation of these dimers and no long-range order of the position of these dimers? Well, it turns out for this simple model, the answer is no. And this was actually proved in an earlier paper by Heilmann and Lieb from 1972, in which they show that for this model over here, where I just put dimers on the lattice as such, there are no phase transitions. The fact that there are no phase transitions means that the qualitative behavior of the system at high density is the same as the qualitative behavior of the system at low density. And at low density, there certainly is no orientational order of any kind. So since there are no phase transitions, there can be no long-range orientational order. You cannot find yourself in a position where most of the dimers end up being vertical or horizontal for this model. So in this paper in '79, Heilmann and Lieb introduced a tweak to this model in order to try and favor orientational order. And the way that they did this is by introducing an interaction between the molecules in this model that is stronger than just the hardcore repulsion of these dimers. And the interaction that they introduced, they actually introduced several different interactions. And this is one of the interactions that they were considering, is one that well, necessarily has to favor alignment of the molecules, because without the interaction, we know that there is no long-range order in the orientation. So if you want to force long-range order in the orientation, then an interaction should be introduced that will favor alignment of molecules. And what this interaction is, it's a small attractive force between nearest neighbor molecules. And the idea is that if you have two molecules that are both adjacent and aligned, what I mean by adjacent and aligned means that these molecules should belong to the same column or the same row, and they should be next to each other, and they should be aligned. So if you have, for instance, two vertical dimers here that are right next to each other, they're associated with a small they're associated with an attractive force over here. If on the contrary, I have a vertical dimer and a horizontal dimer, there is no attractive force between them. Or if I have two different columns of vertical dimers, there are no attractive forces that go from one column to the next. So with this interaction is going to favor alignment. And so given that without the interaction, there is no long-range orientational order, the first natural question is there orientational order for this problem? And this is what Heilmann and Lieb proved in 1979, that for this model, with this interaction, there is long-range orientational order, which means that if you look at samples of configurations in this model, most samples will either be mostly vertical or mostly horizontal. So have mostly vertical dimers or mostly horizontal dimers. But that's only half of the picture that is necessary to prove in order to show that you have a liquid crystal phase. To have a liquid crystal, you need long-range orientational order, but no positional order. It shouldn't be a full crystal. And the technique that Heilmann and Lieb used to prove this, which is based on reflection positivity and so-called chessboard estimates, was just not suited to prove the absence of positional order. And so they weren't able to complete that proof in '79, and they formulated a conjecture that it should be true, but they were not able to prove it back then. Now, since 1979, things have progressed, and other results have been proved about liquid crystals. In particular, there have been other models other than the Heilmann-Lieb model that were introduced, and in which the existence of a liquid crystal phase was proved. The earliest such model that I know of appears in a paper by Brickmont, Kuroda, and Leibowitz from 1984, where again, it's a simplified model. It's again a planar model, so a model in 2 dimensions. And the molecules in this model, they live in the continuum. They live in R2. They're not living on a lattice. However, the orientation of these molecules is discrete. So just for the sake of clarity, think that these molecules can either be vertical or horizontal, similarly to the dimers in the Heilmann-Lieb model. For this model, Brickman, Kuroda, and Leibowitz showed that there would be a liquid crystalline phase, which is a great achievement. Although, sorry, one thing I didn't mention about this model, the molecules are approximated by hard needles. What I mean by needle is an object that is infinitely thin. And since that object is infinitely thin and you have a discrete set of orientations, whenever you find yourself in a phase in which most of the molecules are, say, vertical, then those vertical molecules, they don't see each other. They never interact with each other because the thickness of these molecules is 0. And since they never interact with each other, it's kind of guaranteed by the model itself that there will be no long-range positional order. There couldn't be any long-range positional order in this system because aligned molecules don't interact with each other. In this sense, this model is very similar to a Whittaker-Allinson model, if you're familiar with such things. So later on, another model that in which rods ended up having thickness was introduced in 2006. This is a model, again, on Z2, so we're going back to a situation that's closer to the dimers, except that the main difference with the dimers in this model is that the size of the molecules, instead of being a single dimer, the size of that of the molecule could be longer. And in fact, in this model, there's several different molecule sizes that are coexisting with each other. And the relative probabilities of finding the different lengths in this model are tuned in such a way that the model introduced by Jauslin and Zarodnik is integrable. Integrable means that pretty much everything that I would like to know about the model, so for instance, the thermodynamic quantities, the partition function, all sorts of quantities related to this model can be computed explicitly. And by computing these quantities explicitly, Jauslin and Zarodnik were able to show that there is a liquid crystal phase. But this model, in some sense, is rather special because it's integrable. So it has this extra structure that's put on top. If we go forward to 2013, there was a paper by Margherita Di Sartori and Alessandro Giuliani, where now they considered, again, hard rods on the Z2 lattice, but without this integrability of the Jauslin-Zarodnik model. So the model that they considered is a model, again, on Z2, where instead of dimers, we're having long molecules, but the length of the molecules is fixed. And by fixing the length of the molecule, there is no integrability in this model. And they were still able to prove the existence of a liquid crystal phase. Now, but all of these models that I've talked about here that had some rigorous proofs associated to them, they're all in 2 dimensions. There's, as far as I know, only one result in 3 dimensions of a microscopic model for molecules in which there's a liquid crystalline phase, although this is not a model about hard rods. So this was published in a paper, in a joint paper of Margherita Di Sartori, Alessandro Giuliani, and myself, which came out some point last year, where we're proving a liquid crystalline phase, but instead of having rods on a lattice, we have so-called plates. What I mean by a plate is, if you think of a rod as being a stick, a plate would be something like a 2x4. So it's a parallelepiped that has thickness, width, and length. And the idea is that this parallelepiped is very long, the width is fairly long, and the thickness is fairly small. And what we showed is that here you have some form of a liquid crystalline phase. So you have long-range orientational order, but no positional order. Now, however, the main limitation of all the proofs that we have nowadays is that the orientation of these molecules is discrete. In every single one of these cases, there's a discrete, the rotational degree of freedom of the molecules is a discrete rotational degree of freedom. And this is crucial to having these proofs work, because it's, well, simply because it's a lot easier to show that there's long-range order in a degree of freedom that is discrete rather than a degree of freedom that is continuous. Okay, so there have been other models since the Heilmann-Lieb model that were introduced in which liquid crystalline phases have been proved, but still the Heilmann-Lieb model remained an open question, so it remained an open question for a long time. And there have been some progress in proving the Heilmann-Lieb conjecture. There was most notably a somewhat recent paper by Diego Alberici from 2016, where Alberici can consider this Heilmann-Lieb model, so with the dimers on the lattice, although he introduced a tweak, which is essentially, you can understand as that tweak being the addition of a large magnetic field in the system. So the idea is that in Alberici's model, there's an a priori term in the energy that favors, say, vertical dimers rather than horizontal dimers. Now it's not a terrible approximation if you think about it, because Heilmann-Lieb already proved in '79 that there is orientational order. And so since there is orientational order, most of the dimers should be vertical or horizontal in the first place. So by favoring, say, vertical dimers, you shouldn't really be changing the model so much. But still, it's a different model. Anyways, for this this modified model, Alberici was able to prove the existence of a liquid crystalline phase. But for the original Heilmann-Lieb model, there still until about 2017 there was no proof. Even though, so this is a numerical paper by Papanikolaou, Charlier, and Fradkin, seemed to indicate quite clearly that there should be a liquid crystalline phase in the Heilmann-Lieb. And the main result that I'll be talking about today is that Elliott Lieb and myself, we revisited this problem and we proved the existence of a liquid crystal phase in this Heilmann-Lieb model. So we proved the Heilmann-Lieb conjecture. So I'm now going to state our result and show you how we approach such a problem and how what kind of mathematics pop up. And in order to do that, I'm first going to introduce some notation and tell you a little bit more how we approach the problem. So the idea is that we're thinking of a system of molecules on this lattice, and what we're going to be focusing on. So what we want to show is that these molecules will spontaneously form a liquid crystalline phase, namely that they'll spontaneously align, but there will be no long-range order in their positions. What I mean by spontaneously align, from a mathematical point of view, means that by introducing some sort of a dynamics, I'm going to look at stationary measures of that dynamic. So I want to think of the system as being in equilibrium with itself. Now, to do this, from a mathematical point of view, means that what I'm going to be considering is a probability distribution on the set of configurations of these dimers. This probability distribution is called the grand canonical Gibbs measure, which will be familiar to all of you who are familiar with statistical mechanics. Now, I'm going to define this Gibbs measure, and really what I'm doing here is I'm introducing the relevant notation for this model. And the way that I'm going to define this Gibbs measure is by defining the average of an observable. So let's take an observable A. An observable is just a function that maps a configuration, a dimer configuration, to a real number. So I take an observable A, and I'm going to define the average of this observable A. So what do I have? First of all, in order to define this and to do everything rigorously, I'm going to cut off my lattice. So I told you that we're considering a lattice model that is based on Z2. Well, to define this measure rigorously, I'm going to restrict my attention to a finite subset of Z2, to a finite square box in Z2, which I'm going to denote by lambda. And the idea is that I compute whatever I need to compute, and then at the end of the day, I take the limit in which the size of the box goes off to infinity. Now, okay, so how am I defining the observable before I take the limit? So I have this sum over here. This is a sum over delta in omega. Omega will be the set of dimer configurations. So this is the set of configurations of dimers on the lattice that are such that no two dimers can occupy the same vertex. And underline delta will be a dimer configuration. Okay, so this is just a sum over configurations. Then I evaluate the observable at that configuration. And then I have here a parameter z, which is a parameter called the fugacity, which is a non-negative parameter, which is raised to the power delta. This absolute delta is the number of dimers in the configuration. Now, the role of this parameter z is to control the density of dimers in the system. To understand this more clearly, you can look at the extremal cases. So if you take z to be very small, right, then z to the power delta will be extremely small whenever the number of dimers is large, which means that the relative probability of a configuration with many dimers is going to be very low. So if z is small, then the density should be low. Conversely, if z is very large, then the relative probability of configurations in which delta is very large will be much higher. So if z is large, I'll have a high density. So z is a parameter that allows me to tune the density. And finally here, I have an interaction term. So this is this interaction corresponds to this little red interaction term that I drew over here. Okay, so this interaction is a pair interaction. It involves pairs of dimers. So I take the product over every pair of dimer in the dimer configuration. And for every pair, I assign this weight, which is e to the j times this indicator function. This is the indicator function that delta and delta prime are adjacent and aligned, that they belong to the same column or the same row, and that they're next to each other. J is going to be the interaction strength. That tunes how strong this interaction is, how attractive the interaction is. And J is going to be taken to be non-negative. The idea again being that in a configuration in which this indicator function is equal to 1 a lot, the relative probability of that configuration will be very high. Will be high provided J is large enough. Now there's a factor 1/2 in addition to this. This is simply because when I take the product over all pairs, every pair appears twice. So I get this extra factor of 1/2. So this is the basic setup that I'm looking at. So I have a random distribution of dimer configurations that each have this probability that is over here. Oh, and this, sorry, I forgot to mention this factor 1/xi is just a normalization to make this a probability distribution. Now there's one thing that I haven't told you. There's this index v that appears over here. The reason that this index v is there is that since we know from Heilmann-Lieb that we have long-range orientational order, that means that most dimers will either be vertical or most dimers will either be horizontal. Now we know from general results in statistical mechanics that what this means is that this probability distribution, the grand canonical Gibbs measure, is actually going to be the convex combination of two extremal measures. And in each measure, I'm going to have either mostly vertical dimers or mostly horizontal dimers. And for the sake of simplicity here, I want to focus on the measure in which I have, say, mostly vertical dimers. I could do the same with mostly horizontal dimers. Though that's a bit of a technical assumption, which would not really be needed if we wanted to do the problem without imposing and without favoring vertical dimers. We would be able to, but this, anyways, is a very mild very mild assumption. So the way that we're going to select this extremal measure with mostly vertical dimers is by imposing a boundary condition. And the way that we're going to impose this boundary condition is depicted in this slide. So what we do is we fix a length scale. So this is something that depends on the parameters of the model, J and Z, and it's a length scale L0. This length scale will actually appear several times in the following, so it's something that is actually quite important. And then what we do is we look at a strip at the very top of the lattice that is of height L0, and a strip at the very bottom of the lattice that is of height L0. And what we impose is that in both of these stripes, there are no horizontal dimers. There can only be vertical dimers. And by imposing this condition, we're imposing that we have vertical dimers on the boundaries, and that ends up affecting the entire system throughout the bulk. Now, this is quite a non-trivial fact, given that we're taking here the thermodynamic limit in which the size of the box goes to infinity. So when the size of the box goes to infinity, the distance between the bulk and the boundaries is actually going off to infinity. So by imposing something on a boundary that ends up being infinitely far away from the bulk, I can still select inside the bulk the vertical phase. So this is a fairly non-trivial statement. So now let me take you through our main result. So this is a bit of a technical slide, and I'll go through each of the statements one by one. Essentially, what our main theorem about this model is that we have a liquid crystal phase. So we have long-range orientational order and no long-range positional order. So let me explain how that appears in this theorem. So the first important bit about this theorem is the range of parameters that we're looking at, which is up here. This range of parameters, some bits of it are natural and others are not. As I mentioned earlier, Heilmann and Lieb proved that if there is no interaction, then there is no long-range orientational order. So we must have some interaction. So it's not so far-fetched to think that this interaction should actually be somewhat large. So the condition that J be larger than 1, J, remember, is the interaction strength. It quantifies how strong the interaction is. So the condition that J is large is not so far-fetched. Now, remembering that the fugacity Z, this parameter Z, controls the density of dimers, the fact that the density should be large is also not so far-fetched. The idea being that if you don't have a large density of dimers, you could have very few dimers that are perfectly isolated from each other. And if they're isolated from each other, there's no reason that there should be long-range orientational order. So the fact that Z should be large is also somewhat natural. However, in here, there's an extra condition that J must be much larger than Z, and that is not really a physical condition. That's more of a technical condition that we had to impose in order to prove this theorem. So this is a bit of a restriction of the model. And in fact, if you look at how things are defined, a more natural condition would be to say that the exponential of J should be larger than Z. In this case, we're imposing that J is larger than Z. So it's somewhat of an unnatural assumption, but this is where we were able to prove things. Now, specifically, what were we able to prove? So the way that I'm going to approach the existence of a crystalline phase here is by looking at specific observables. Namely, these observables are going to be of the form of this bold 1 index E. This here, if E is an edge, is the indicator function that there is a dimer at that edge. So if I fix now a vertical edge EV, this quantity over here is the average of the indicator function that there is a dimer at E. Quite simply, it's the probability of finding a dimer at this given edge E. Now, the first thing that we can prove about this is that this probability is independent on the location of that edge. And that probability, which doesn't depend on the location of the edge, is equal to 1/2 plus a small correction, right? When J and Z are large, this correction becomes very small. Now, 1/2 is a pretty good score, given that every dimer occupies 2 vertices. That means that the maximal density that I can possibly have is 1/2. So in fact, the sign of this correction over here would be negative, right? 1/2 is the maximal density that I could possibly have. So what this statement is saying is that the probability of finding a dimer somewhere is independent of where that somewhere is, and that probability of finding a vertical dimer is almost the maximal probability. So this contains orientational order, because by just imposing vertical dimers on the boundary, which remember is infinitely far away, I've made it almost certain that given an edge, that edge should be occupied by a vertical dimer. It's because since 1/2 is the maximal density. So it's almost certain that vertical edges are occupied. So that's long-range orientational order. Now, as far as absence of positional order goes, the fact that the probability of finding a dimer at a vertical edge is independent of the position of that edge, that's already a good sign. If that weren't true, then we'd be in trouble. But it's not actually good enough to prove absence of positional order. right? You could find yourself in a situation where this Gibbs distribution is a convex combination of two distributions, each of which has positional order, but each of which is a shift one with respect to another, in which case in the total distribution, I would still find a probability of finding a dimer independent of the position, but still have long-range positional order. To exclude that possibility, what I compute is this, this observable here, which is a truncated correlation function. What I have here is the joint probability of finding a dimer at E and a dimer at F minus the product of the probabilities of finding a dimer at E and F. So this is the truncated two-point correlation function for this model. And what we find is that this truncated two-point correlation function decays exponentially with the distance between these two dimers. And this distance is this distance subscript HL is a distance that is generated by this norm. The basic idea of this distance is that in the horizontal direction, the distance comes with a prefactor j, which is very large, whereas in the vertical direction, it comes with a prefactor e to the minus 3/2 j is e to the minus 1/2. This, I'll recall, is the inverse of this length scale over here. So it comes with this prefactor, which is very small in the limit that we're considering in the vertical direction. So this means that I have exponential decay of correlations, but the rate of decay of correlations is very anisotropic. In the horizontal direction, the rate of decay is j, so very large, very strong decay in the horizontal direction. But in the vertical direction, the rate of decay is this one over here, which is very small, which means very weak decay in the vertical direction, which means that there is exponential decay in the vertical direction, but with a very long correlation length. So dimers that are closer than this very long distance end up being quite correlated. It's only at very long distances that you lose this correlation. So these are all statements about vertical dimers. I can make similar statements about horizontal dimers. So if I look at the probability of finding a horizontal dimer somewhere, again, that probability is independent on the location of the dimer, and the probability of finding a horizontal dimer is very low. If I give you an edge, a horizontal edge, the probability that it's occupied by a dimer is very small. Similarly, I don't have any long-range positional order between two horizontal dimers. And in addition, since this slide was already full, I didn't write it down, we also have a similar result about the truncated correlation between a horizontal dimer and a vertical dimer. So overall, this theorem shows that there is orientational order in this model, but no positional order. Now, let me tell you, okay, so this is our main theorem, and this implies the existence of a liquid crystalline phase. Now, let me tell you just the basic idea of how we prove this theorem, and I also want to show you where this parameter in the Heilmann-Lieb distance, in the HL distance, came up, why we have this extremely long correlation length in the vertical direction. So the idea of the proof is the following. Heilmann-Lieb tells us that we should either mostly have vertical dimers or mostly horizontal dimers, and if we impose vertical boundary conditions, then we should mostly have vertical dimers. Now, if I look at the case in which I only had vertical dimers, so no horizontal dimers at all, then I end up with a system that's actually integrable. Because if I only have vertical dimers, I find myself with a system in which all the columns are independent of each other, because dimers are all contained within a column, and the interaction between dimers is also contained within that column. So I can consider each column independently, and each column is a one-dimensional model, and I can solve that one-dimensional model exactly. And in particular, I can compute all of these. These quantities. So what are these quantities that I wrote on the slide over here? They're the same as the quantities over here for the full model, except they're written for the model in which I only have vertical dimers. And what I find is that these quantities, they have essentially the same values as they had in the theorem. So the probability of finding a vertical dimer at a given edge is approximately 1/2. And the correlation function between the positions of two dimers decays exponentially with this very same rate. So again, this means that in this one-dimensional model, dimers are decorrelated at long distances, but the correlation length of these dimers is extremely long. It's the inverse of this distance. It's the L0 that we had before. So this, first of all, implies that the rates that we have in this theorem, which a priori are only bounds, should actually be close to the optimal rates that we find, because for the purely vertical model, for the model where there are no horizontal dimers, I already have that very bad decay rate. And the main idea of the proof is to make the idea that I told you at the beginning of this slide rigorous. So namely to say that, well, if we know that we should mostly have vertical dimers, then the observables for the system with only vertical dimers shouldn't be too far off from their values when I introduce a few horizontal dimers. Now, making this rigorous is not such a trivial thing, and the idea is to change the focus from dimers to a more macroscopic object. The idea being that what we want to prove is that there aren't too many horizontal dimers. And how do we go about proving such a thing? Well, the basic mechanism for which there would be no horizontal dimers is that if I have vertical dimers and horizontal dimers, then I'm going to have an interface between a vertical phase and a horizontal phase. And now the presence of this interface will come with a probability cost. Why does this come with a probability cost? Well, if I find myself inside one phase, so let's say that I have no horizontal dimer, everyone is vertical, the density is very high, which means that most sites are occupied. So here for the drawing, since I wanted to show that there are monomers, there are many more monomers than there would be within the range of parameters that we're looking at. So you should think of most sites as being occupied by dimers. And if most sites are occupied by dimers, that means that essentially half of the vertical edges should be associated to an interaction. So I should have a little red squiggly line on essentially half of all of the vertical edges. But now when I have an interface, you see, wherever this interface is going, so wherever this loop is going, whatever edge it's crossing, those edges are going to have no interactions. They're going to have no red squiggly lines. And which means that if I have a loop of length L, so a loop of length L is a loop that crosses L edges, I'm going to have to cut L red lines. And what is the relative probability of cutting L red lines? Well, half of the edges should correspond to a red squiggly line, and each red squiggly line comes with a probability weight e to the j. So if I cut L lines, I should end up with a relative probability that is proportional to e to the minus 1/2 j times the length of the loop. And if j is large, which is the case here, the probability of having a loop should be very small. And in fact, the probability of having a very long loop should be even smaller. Now, when you start seeing things in that light, things are starting to look good, because I started out with a model of dimers, which had a lot of microscopic degrees of freedom. They can jiggle around a lot, but it's also a high density model of dimers. So I have a lot of dimers that are interacting strongly with each other. However, if I consider now if I replace the dimer model by a loop model, by just focusing on where these interfaces are, I find myself with a model of loops, and each loop has a very low probability, and the probability of a loop of length L decays exponentially with the length of that loop. So that means that I should have a very low density gas of loops. And a gas of loops is something that I can easily control using a technique called the cluster expansion. Now, there are some significant difficulties that come with this. The main issue with this loop model is that also there are two difficulties. Let me actually focus on the second one first, because that's easier to treat. So the difficulty is that this loop model is an interacting loop model. And why do these loops interact? So one of the reasons is that there are actually two kinds of loops. There are loops that separate vertical dimers outside from horizontal dimers inside, and loops that separate horizontal dimers outside from vertical dimers inside. And these loops are not necessarily the same. For instance, where's the slide here? This loop over here could only be separating horizontal dimers outside from vertical dimers inside, because the geometry of the loop is such that it wouldn't fit to put a horizontal dimer inside. So this means that there's an interaction between loops that are contained within each other. A loop that separates vertical from horizontal should contain loops that separate horizontal from vertical, and so forth. And this actually introduces a long-range interaction between loops, which is, thinking of this gas of loops as a gas, long-range interactions are terrible. However, this particular problem is solved in a somewhat standard way using a technique called Pirogov-Sinai theory. So that's something we could deal with. The more difficult aspect of the proof comes from the fact that loops are separated by dimers, right? The idea is that a loop is an interface between vertical dimers and horizontal dimers. But if I look, say, at these two loops, I'm going to have vertical dimers between these two loops. And now, what I told you earlier is that these vertical dimers, they decorrelate over long distances, but the correlation length is very long. So this means that these loops are actually going to interact with each other with a weight that decays exponentially as the loop move away from each other, but the rate of decay of this exponential is very small. So the correlation length is very large. So one has to tweak this Pirogov-Sinai picture to accommodate the fact that this gas of loops is actually a strongly interacting gas of loops. And now, just to finish, I see that time is running. Let me just conclude by showing you this parameter space. So these are the parameters in the model, Z and J. I just wanted to leave you with a comment on what's left to be done. What we proved is we proved the existence of a liquid crystalline phase in this part of the parameter space over here, in the red part of the parameter space. However, in the Heilmann-Lieb 79, they proved orientational order in this entire part of the parameter space. So there's a lot of Z's and J's that haven't been covered by our theorem, for which the problem is still open, and so there still is work to do on this. And on that, I will thank you very much for your attention, and if you have any questions, I'd be happy to answer.
Well, I think before we ask any questions, we should thank you for a very beautiful exposition, Ian, and unmute and clap. So are there questions? Can you raise your hands if you have a question? Raise your hand electronically. Kaifeng, you have a question? Kaifeng?
Yes, I have a question.
Yes.
Yeah. Sorry, could you please go to the page 8, the formula of the
Yes.
partition one? Yeah, this one. So, for example, before you take in the limit, well, here you can simply take the observable A to be, for example, the simply the case like A is equal to infinity, right? And then
Yes.
before you take the limit lambda go to infinity, let us consider a finite like n by n lattice. So you can simply consider this formula as a polynomial of the parameter of Z.
Yes.
Yeah. So my question is that if you fix the interaction strength, do you know the location of the zeros of the complex zeros of the Z?
Of the partition function, yes. So, right, that's a good question. So the question is if, right, so if I just look at the partition function, which essentially means if I just look at this psi here, do I know the location of the zeros of this psi? I don't know the location of the zeros of this psi. What our proof provides is a bound. So the idea of our proof actually reduces to an expansion of this quantity over here in powers of 1 over z. And by expanding in powers of 1 over z, what we're showing is that the log of the partition function is an analytic function of 1 over z when 1 over z is smaller than a certain radius. So that in particular means that the zeros, so what we're imposing are bounds on the locations of the zero of the partition function. We're saying that the zeros of the partition function have to be inside some large circle in the complex space corresponding to z. So I can't tell you the exact location of the zeros of the partition function, but the way that we prove this theorem as a corollary shows that all the zeros of the partition function have to be inside some very large disk in the complex z plane.
Well, do you have any like result about this complex zero outside of some like disk?
So in fact, for this model, it's easy also to find a lower bound for where the zeros have to be. The idea being that when you find yourself at low density, you can use the cluster expansion just straight and show that you will have a lower bound. So so if you combine the lower bound and the upper bound, what I can tell you is that the zeros are going to be inside an annulus.
So Lenny Gross, did you have a question?
Yes. If you impose conditions on the lateral edges, such as either vertical or horizontal in some band, will that help or make the problem tremendously harder?
So if in addition to the vertical bands, or
yes,
that shouldn't change much. So the boundary condition that we chose over here, we actually chose it in order to make the proof simpler. So it was essentially so the way that we go through the proof is by using an induction where essentially we're computing the partition function inside loops, and we want the partition function inside loops to look similar to the partition function on the whole space. That's not a necessary condition. So we can actually consider much more general boundary conditions than the one that we considered over here. That shouldn't matter. As long as the boundary is imposed in such a way that vertical dimers are heavily favored, so adding bands on the side. Oh wait, sorry, what's your question, that on the bands on the side you only have horizontal dimers?
Well, that's a choice up to you. Either way, it might influence the outcome.
Right.
So I think what you're saying is that if you choose on the side boundaries more vertical
right.
Dimers, that will not change the mechanisms of proof or
right.
the results.
That's right. If we had horizontal dimers on the sides, though, that would change everything.
Yeah.
And in fact, it would mix the two measures, and we would no longer be in a situation where most dimers would be vertical. We would be in a situation similar to the Ising model with so-called de Bruijn boundary conditions, where we would have an interface between a horizontal phase and a vertical phase.
Yeah, depending on the strength or width of the lateral horizontal set of dimers.
That's right.
So I have a related question. Have you then proved the existence of this other type of phase transition, the phase separation, which is true in the three-dimensionalizing model, but not in the two?
Right. So for the type of phase transition that you're talking about here, I suspect is that for the Ising model, you have a difference. So if you impose a boundary condition where on half the space you have plus spins, and on the other half you have minus spins, you have an interface, and the behavior of this interface actually depends very strongly on the dimension. In this model, we haven't investigated. We don't really know, and it seems like that should presumably be quite difficult to control the geometry of this interface and the fluctuations of this interface. Yeah.
Well, your proof, I mean, your description of the proof, I'm not sure of all the technical details, but just listening to you, it sounded very much an outline like the Parles argument.
Right. It's a somewhat more, so it's based on the Parles argument, but the main difference between the Paris argument and our proof is that in the Paris argument, there are no interactions between the
Now, you
different
mentioned in Eliot's old paper that he used reflection positivity, but you didn't mention that in your talk today. Does that come into your?
That's right. We do not use reflection positivity at all. The idea of the Heilmann-Lieb proof from 79 was to reduce the problem. So the problem is a fairly global problem on this very large lattice. And the idea of using reflection positivity is to reduce the problem to a local problem. So what they were able to show is that if you look at a small square, that is just a 2x2 square, the probability of finding a horizontal dimer and a vertical dimer inside that small square actually gives you a bound on the probability of finding horizontal dimers in the whole space, and that's based on reflection positivity. Here, since we're focusing on really absence of positional order, that sort of method was not really available to us, simply because when we're thinking about absence of positional order, in this model, we do have positional order over very long distances. It's only when you look beyond this very long distance that you lose positional order. So this idea of reducing the problem on the big lattice to a small local problem wouldn't work in this case, because this small local problem, the small local box, would have to be at least as big as this very large correlation length. So that's why reflection positivity doesn't really work to prove the absence of positional order here. And
so if you are not using reflection positivity, then you're probably also not using chessboard estimates, right?
Exactly, no chessboard estimates. It's much closer to Peierl's argument than to a chessboard estimate.
Mm-hmm.
And paragraph-Sinai. And in fact, John Embry in his thesis developed the paragraph-Sinai theory in several directions. Maybe those techniques are also useful for you.
Yes, absolutely, absolutely, yes. It's related to all that. This is a somewhat, so the thing that makes paragraph-Sinai theory a little complicated here is that we don't have a finite number of ground states. We have an infinite number of ground states. And whenever that happens, usually the general applicability of paragraph-Sinai suffers.
So another situation in which there are infinite number of ground states is in the case of continuous symmetry, and then infrared bounds come in. Is there something like infrared bounds in this case?
For our proof, there aren't. Infrared bounds are also, one thing that one of the strengths but also weaknesses of our proof, I guess, is that we could actually tweak the model in a number of different ways. So we could have next nearest neighbor interaction. It wouldn't change much. So it's a somewhat robust proof, but on the flip side, that means that we won't be able to get as much as what one would get with these techniques like the infrared bounds or like the reflection positivity, which are a little more sensitive to what the details of the model are.
Does anybody else have questions? I see Jinsum Wu is here. Are you actually? Oh, but you're not on the audio. So see, Elliot is here. Do you have anything to comment on, Elliot?
Oh, well, no, I join you in admiring Ian's delivery. It's fantastic.
Absolutely. So I think if there are no other questions, we should once again thank Ian for really wonderful delivery, inspiring talk, and a very interesting set of problems that you described.
I second Elliot's view of that delivery.
So give you another round of applause. So we're planning to continue this seminar every week, and this time is to make it available to a wide audience. I hope that if there are comments about the time or the subject, send us email. Thank you. Bye-bye.
Thank you very much.